Let me just pull the presentation. It's not going to be on. Can you see my screen?
Not yet.
Okay. Ah, not again.
Yeah.
All right. Right. This. Excellent. It works.
Yes.
All right. So it's a follow-up to the electrochemical presentation that I did this morning. So we're going to go over 3 examples. One about the reduction potential in regards to silver chloride reference electrodes. One about the simulation of the anodic component of the cell, and one about the cathodic component of the cell. So that's pretty much what I have for you this evening. So for the first example, for the calculation of reduction potential, the objectives of this example is to evaluate the standard reduction potential as a function of temperature for certain metals when compared to a reference. This will allows us to establish a strategy for electrode refining process, since we're going to have an idea of which metal can be reduced first or oxidized first. So basically, the reaction that we're going to use, because it's going to be in the reaction module, is silver in its solid state, a certain chloride out of a certain metal. It depends on your system, and that will be transformed into the metal. That will be reduced into the metal, the silver chloride. And what we want to know basically is what is the potential for this reaction. So, as I said, this is the reaction that we're going to go with. This example treats aluminum specifically, but it's the same thing that we're going to do if we want to do magnesium, manganese, or any other elements. So first, what we're going to do is that we're going to use this window, this reactant window in the reaction module. We're going to fill in this window to represent the reaction that we got going on. And we're going to get this result, which is the delta G divided by the number of electron used and Faraday constant. So to do this, well, we input in this window our references phases and our species and the stoichiometric composition of it. And then we select in the output, we select that we want it in volts, and you can see what is the formula for this. For aluminum, it was 3 electrons. You can change it by going over the 2 electrons and changing it to 2, 1, or 3 or 4, depending on what you're looking at. And then you can input there the temperature. It works the same way that it works in the equilibrium window. So if you want to do multiple temperatures, you can do the triplet with the starting, ending, and the steps increment, and it would work the same way. So what you get, I did only one temperature here for the example, but you get 892 millivolts for this specific reaction. So what is interesting, now that we know how to do this, we can do it for a bunch of different metals, which would be some of the impurities that we've seen, or the alloying elements for aluminum alloys, and we can do it for all of them, and we can rank them according to their reduction potential. And what we need to understand from this is that the most negative reduction potential will be oxidized at the anode if we run an electrolysis cell. And the easier, the lower it is, the easier it is to oxidize. So let's say that we have some, as Anya presented, let's say that we have some aluminum and we have some magnesium. We will preferentially preferably or proficient, blah blah. The word, you know the thing, and you will get the mag out much more easily than you would get the aluminum out. And on the contrary, the elements with the more positive reduction potential, if they are present in the electrolyte, which means in their salt form, they will be reduced at the cathode before. So let's say that we have a certain salt that has sodium chloride, lithium chloride, mag chloride, and aluminum chloride. The aluminum would go out first uh, according to the standard potential. But this is not what happens in reality when you have elements that are very close. As you can see, like this, when we analyze this, we can see that we have the potential to probably remove manganese before we remove aluminum by just doing a simple salt flux or something like that. And we see that in reality, it's not the case. You will not be able to take away the manganese because of the activity contribution. So it's unfortunate, but we need to strategize better than this. So what I've put in green right there is what are the elements that are present or described in some of the phase, in one of the phase of the FT salt database, because it's really important when we're going to go into the equilibrium module to do the simulation of the anodic component and the cathodic component. If uh, these salts are not present as end members of the molten salt phase, you will not be able to have them in the equilibrium module. So we need to think about this in a way that we need to strategize. So if we know that we have a lot of, let's say, a lot of copper, but the copper is not represented in our salt, we know that most likely, as long as we have a good amount of aluminum, the copper will probably not go into the solution because the difference is too major. So we can this exercise give us some insight as to what will probably go, not go, what can we consider, how can we reduce the size of our system in order to have something that is as close to the reality that we can have. So it's very important to do this exercise. So this was the very short and sweet example on reduction potential, nonetheless very important. So for the second example, as we've seen this morning, we need to simulate both the component of the cells separate. So we will start with the anodic interface, and the goal of the anodic interface is to simulate what would happen if you would to run molten salt electrolysis cell for some UBC plus some other scrap. So it's not going to be the same composition as Anya showed you, but nonetheless, it would be applicable. You would just need to change the composition to put what she found, and it would work also. So, and we want to validate the previously established strategy that we had. So let's say that we think that manganese is going to go. This will show us if it goes for real or not, because this will take into account the activity contribution. So it's the natural process into design the electrolysis cell. So for those that were there this morning, this would be a more complicated process that involves the anodic component, and we have later on we're gonna have the cathodic component. So what we're gonna do here is do this step, do this particular calculation with the metallic anode, the electrolyte layer, and see how much can we transfer from the anode to the electrolyte under a certain amount of a charge transfer. So we're going to start with selecting the three databases that are important for us: FACTPS for the pure gas, FT salt for the electrolyte, of course, and FT light for the alloy. So what we're going to put in is, first of all, our UBCs or scraps. As you can see, I think it's a bit more concentrated in magnesium, but if we'll see the difference maybe another time. The salt layer, I took a standard sodium chloride, lithium chloride salt. It's probably not what they use in the industry. It was just an example. You can fiddle with it. And this, the the silver chloride is going to be our charge transfer agent. We're going to use it to transfer some chloride ions and have delta G, a Gibbs energy differentiation to that we can use to establish what would be the potential of the real cell. And this is what you're gonna go look at when you press next. We need to do the phase selection for this. So this is a phase selection that is a bit more complicated because silver is not really in our system. So we need to simulate the fact that it's not in our system by deselecting all the silver compounds in the gas phase, in the solid phase too. But in the solid phase, what we're gonna keep is solid silver. This way, if we do this correctly, as you might have noticed by now, the only stable phase that contains silver is solid silver. So we know that it's gonna form this. We're gonna force this formation by making all the other phases that contain silver inactive. And by this is the phase selection that I do for the solution. And on the solution that contains silver, what you need to do is remove silver as an end member. What you do is that you right click on the solution right there, and then you would get this menu, and then you click on you click on this on the plus or on the I, the G, depending on what the selection you had, and it's gonna remove it. And you're gonna get a warning, but trust me, it's all right. So you adjust the alpha parameter that represents the amount of charge transfer that you're gonna get, and the temperature you want to do it. I've selected 800 and to make sure that my salt was liquid, and I did some screening on the alpha parameter. So let's look at the result that we have. As predicted, when we start to do the charge transfer, we know that it's most likely is going to be the elements that were lower on the reduction potential series, and it was magnesium. So we know that we can see that the magnesium chloride is getting magnesium is getting transferred to the salt, as we can see by the concentration or the mass of magnesium chloride increasing. But what we can see is that the amount of aluminum chloride increases way before the manganese chloride increases. So when we get the activity contribution, we can see that it's going to be the aluminum that's going to oxidize before the manganese. So this tells us that we will not be able to remove the manganese by electrorefining this alloy. What we can observe too is that we see nowhere near, we don't see on our graph that iron was oxidized, which means that everything that is over iron should not be significantly oxidized either. And everything that is in between iron and aluminum, for instance, we would need to do some more literature review to see if it does or it doesn't oxidize in this instance. So what we need to do the cathodic component is that we need to take some sample of the salt at a certain point. So we can see that at alpha equal 50, we can see that we have some aluminum in the melt, and what we want to do is to conserve the aluminum at the anode. So what I'm gonna do is I'm gonna take the salt at alpha equals 25, so that we have we don't have much aluminum and mostly just mag chloride. So we get to the third example, which is the cathodic component. And what the objective is the same as before, is to simulate the cathodic component of the molten salt electrolysis cell and validate our strategy. So we're going to validate that the cell in itself works fine on its totality of its component. And we're going to witness also the activity contribution of what happens when the activity changes too much. So then again, you see the big process flow sheet. And what we're going to focus on this example is this simple calculation. And we do most of the, what we're going to do at first is we're going to save the stream as you've seen in countless example today. And what we're going to save is the salt. So you need to save this while you are on the page a equals 25, as we can see right there, because it's going to save the phase according to the page that you are, the result page that you are. So it's important. And then we're gonna import it in the next calculation. And this example is a bit more simple in term of reactants. All we have is we put silver instead of silver chloride, and we put the salt. So what we're gonna do is all of the same thing. This is like all the silver containing compounds, and what we're gonna do is in the pure liquids, we're gonna keep the silver chloride compound, and in the solution, we're gonna move all the silver end members. And then the same thing, we adjust the alpha parameter that represent the charge transfer and the temperature. I put the same temperature, and I changed the alpha parameter because it's not 1:1. There's a certain ratio in between them to have the same amount of coulombs that you pass from the cathodic to anodic part. But this is just an example. And what we can see when we screen the alpha parameter, the charge transfer, we can see that when we first start, it's principally the mag that is reduced at the cathode. And since it wasn't the most electropositive, the most positive reduction potential, as we can see, we have a certain amount of aluminum and manganese that should reduce before mag, but their activity is so small that it doesn't occur. The reaction is not preferential to just reducing the mag. And we can see that we can have a high purity mag if we do this. And what happens if we deplete and we have too much of a charge transfer before we replenish the electrolyte? We can see that we're gonna have deplete all of the mag chloride, and we'll start to reduce some of the lithium and some of the sodium. But in reality, it is safe to assume that this is not gonna happen, because both the anodic and the cathodic component happen at the same time. You need to go back and forth, as we've seen this morning. So in conclusion, I hope that these example helped show what I was trying to show you this morning, and consolidate some of the concepts that we've seen. The reduction potential theory can provide a lot of insightful information during the design process stage, as we can establish a certain strategy with the scrap that you have. The activity is important to consider in order to properly assess the electrochemical process. So as we've seen, our first strategy was to probably remove the manganese, but we ended up not being able to do it because of the activity consideration. ChemApp is a wonderful tool to simulate complex unit and electrochemical process due to the nature of having two components in the cell. And as we've simulated, demagging of UBC could be a viable process via electrolysis to obtain high purity magnesium. Thank you very much for this, and I'm open to your question right now.
Thank you so much, Francis. So I'm happy to present this type of calculation that can be done using FactSage. So basically, there's a way now, an indirect way to be able to evaluate these oxidoreduction reaction that happen inside electrochemical processes. Like I've mentioned previously, we have a paper going on the FactSage application, and we've presented an application where we're producing aluminum using the ALRU process. So we'll have a chance to see how we can perform all these calculations and obtain different useful parameters of interest for this process. Okay, Eve, are there any questions or comments for this presentation?
I don't see any questions at the moment.
Perfect. So I think I don't know if you can activate Arthur's or Chris' microphone. I don't know if they can see.